person invests $4,000 in stock today, and the value triples every 15 years. Let V of t be the value in the account t years after the initial investment. Find an equation. All right, well, this one's slightly different than what we had before. Let's make a little table here. So we're starting with $4,000. Oops. We're starting with $4,000. I should have written it that way. 15 years later, our account will triple, which means we'll have 3 times as much. Another 15 years, the account will triple again. And then in another 15 years, of course, it will triple again. So you see we're getting the exponential function. We've got 3 to the 1, 3 squared, 3 cubed. The difference is it's every 15 years. All right, so the way that happens in an equation is we're going to have V is, our initial value is 4,000. It triples, but if I write this symbol, then it would triple every 1 year. To make it triple every 15, we take the t and we divide it by 15. So now when I plug 15 into this formula, 15 over 15 is going to be 1, and I'll have 4,000 times 3 to the 1. When I plug in 30, 30 over 15 would be 2, so I'd get the 3 squared there, so on and so forth. Determine the value in the account after 20 years. Well, I plug in 20. And I grab my calculator. That's an exponent there, not a multiply. It looks like multiply, but it's not. 4,000 times 3 raised to the 20 over 15. According to my calculator, I get $17,306.99, which seems reasonable because in 30 years it would have tripled. Well, in 15 years it would have tripled. That would have been 12,000, so it had to be more than 12,000, less than tripling again. Seems reasonable. All right, next problem. The world population for various years is given in the table below. Determine, let P of t be the world population, t years after 1970. Determine an exponential regression. All right, so to determine the exponential regression, we need to use desmos. So here's desmos. And then I'm going to cheat a little bit just to save time. I redid the table. T starts at 0 years because that's 1970, 10 years, 20 years, so on and so forth. So I copy this and dump it into Desmos, and it will rescale for me and everything. Have a nice graph. There it is. Now you'll notice this looks almost linear. The reason that is look how big the scale is. This is 5 times 10 to the 9. This is 1 times 10 to the 10. These numbers are so big that the scale actually makes it look misleading, makes it look linear. It's really closer to exponential. All right, so to find the exponential regression, y1, twiddle, wrong button there, twiddle a times b raised to the x1, and it finds the exponential regression. So my answer is 3.825 times 10 to the 9 times 1.01545 to the x. All right, so I'm going to write that down on my paper so I can copy it here, then I'll switch the camera back. So we're going to have P equals 3.825 times 10 to the 9th times 1.01545 to the t. All right, let me switch back here. All right, there you go. Now you can see that. Use the regression, determine the population in 2020. Let's see, 2020 was 50 years since 1970. So I plug 50 into this formula. I'm just going to grab my calculator instead of writing it all down again. 3.825 times 10 to the 9 times 1.01545 raised to the 50, I get 8233009,870. A little over 8 trillion people. Oh, actually a lot over 8 trillion, 233 billion over. That's a lot of people. All right, number 6. Determine an exponential equation of the function given in the infographic below. All right, so again, we're going to need desmos here. I'm going to pause and try to figure out a way to get both desmos and this graph to show up on my screen. I'll be right back. All right, this will kind of work, I guess. This time I have to build this table by hand. So I guess I need desmos a little bit higher to see. Build a table. And then I guess I'll just, I'll call this year 15, I guess. So I'll have 15, and that number is 939,332, I think. 939,332. And then year 20, we have 295,534, it looks like. This is like an eye doctor test for me, kind of. All right, I'm gonna have to scroll up and just type these numbers in here. We have 25, and that one is 61,256. Year 30, 7795. Year 35, 570. And finally, year 40, 20. Now, of course, you're going to notice that these dots fall way down here. This is because in the previous problem our scaling was so big. Let's change our scaling. We need to go up to more than 939,000. So let's make our Y max be, oops, x's, let's see, x's could go from maybe -10 up to 50, and the y's could go -100 up to, it needs to go up to about 1 million, I guess. Let's see how that looks. Yeah, so we can see all of the data there pretty much. You can see I got to make it fit in the video capture window. You can see there's the first one, and then scroll down, fits all the other ones. All right, and then it says find the exponential regression. So again, we would type y1 twiddle a times b raised to the x1. And it computes our exponential regression, and you can see the regression fits pretty well. You do notice here that our b number is smaller than 1 this time. That's because we have exponential decline. When you have exponential decline, your b is between 0 and 1. All right, the last thing I want to talk about in this section is not on your sheet, but this comes up. There's 2 more formulas you're going to see in this section that you're going to need. And the questions are going to look like this. You invest, that way you can see it, you invest, let's say $500 at 3% interest, compounded monthly. How much is in the account in, say, 10 years? Okay, so we did a problem back in video 1 where interest compounded annually, but here interest is compounding monthly. So if your interest is compounding more than annually, monthly, quarterly, daily, whatever, there's a different formula we use, and the formula is A equals P times 1 plus R over N to the NT, where P is still the amount we start with, R is the interest rate, T is time, but N is how many times per year it compounds. So in this case, since we're compounding monthly, N will be 12. So our answer here would be A equals 500 times 1 plus 0.03 over 12 raised to the 12 times 10. And then you would grab your calculator and type that up. 500 times 1 plus 0.03 divided by 12 raised to the 120. That turns out to be $674.68. All right, so this is a formula you'll need, and you'll use this formula anytime you see compounded monthly, compounded quarterly, compounded daily, anything like that. There's one last formula you'll need. Let's say we have the exact same question, but it says compounded continuously. For compounded continuously, you use a slightly different formula, A equals P e to the RT. You should see an E button on your calculator. If you don't see an E button on your calculator, that's all right. E is about 2.71828. So if you don't see an E button on your calculator, you can just use that number. But my guessing is there's an E button on your calculator. So for the same problem, the answer would be A equals 500, E raised to the interest rate is 0.03 times 10 years. You know what this compounded continuously is? This is a hypothetical situation where you're earning interest all the time. It's more than daily, more than monthly, more than, every second. It's at all times. And you'll see from the answer that it doesn't make that much difference. If you could get somebody to pay you interest all of the time, you only made a few more cents. So, okay, well that's it for this section.